Crop scouting is an integral aspect of plant health management. Though different crops require different scouting strategies, the fundamentals are the same. It is fundamental to know what healthy individuals of whatever plants are being grown look like, as well as what pests and pathogens are likely to be encountered, as well as their signs of infestation. Typically, the edges of crops are not representative of their entirety, and so sampling considerations must be made in order to ensure a high likelihood of detection before a pest population becomes unmanageable. The economic threshold is the population level at which a pest should be controlled before production damage equals the cost of pest management. This used to mean simply applying a broad-spectrum chemical compound that was quick and highly effective, and hazardous in many cases, to treat most pests that were predicted to be problematic.
But most pesticides in wide use today fall into one of two general groups according to the reaction they produce. DDT, the most widely used of all economic poisons, is representative of one of these groups. These poisons are slow in taking effect, but may remain active and potentially dangerous for many days or weeks.
Unfortunately, through misapplication and overuse, their viability waned both because they were downright noxious and because resistant populations developed for many pests and pathogen species. In the advent of biocontrol agents and their growing usage, preventative applications are often necessary. Emphasizing preventative over curative treatments means that while overall instances of treatment increase, pest pressure is reduced at its most vulnerable and opportune time, having a greater chance of overmatching the population before it can become close to the economic threshold. However, even with heavily prophylactic strategies, it is still important to assess pest pressure and to evaluate control efficacy. Scouting benefits from an appreciation for statistical sampling methodology and pest bionomics. Sampling in the field typically takes two different approaches I refer to as random and directed. Random sampling is utilized in order to eliminate bias in circumstances where pests are assumed to be encountered at any sample location. Commonly, many pest species are introduced more or less randomly, either on air currents as aeroplankton or by distribution during an egg-laying process, so it is often the default sampling pattern. One advantage of random sampling, aside from its lack of bias, is that the average sample should be representative of an area if enough samples are taken. Directed sampling is utilized with a bias towards certain criteria such as spatial location, time of year, and population dynamics. Many incoming pests are more likely to be found at the threshold between crop borders, depending on the environment, and sampling may provide an advanced warning of incoming organisms, especially if they are traveling short distances. Likewise, some pests are more likely to develop and expand uniformly, such as with some waterborne or soil-borne pathogens and other pests that are not airborne. In the case of their anticipation or detection, it may be prudent to utilize this understanding of their behavior to minimize reaction time and maximize treatment efficacy, especially where biocontrol agents are paramount, by detecting signs as early as possible along an expected pattern. Further, not all crop environments are linear nor homogeneous, and taking into account these details can elucidate patterns and affect scouting protocol for each cultivation space. Whether directed or random, the number of samples should be kept consistent between scouting sessions if they are to be compared, and a definition of what a sample consists of must be outlined. For example, a hypothetical scout group must scout 100 rows of plants. Each row is segmented into 11 1x1 meter square spaces for a total of 1,100 sample units. Let's say that they sample 3 units of every 4th row once a week and rotate so that there is full coverage by the end of the month. This means that they scout 75 units of 25 rows per week, or about 6.8% of the crop per week. In a month, the scouting group evaluates 27.2% of the total crop. Of course, the next question becomes, Is that sample size large enough to be useful? The most relevant answer depends on the particular scope of the scouting and unique contextual circumstances of the cultivation environment. Scouting is always a balance between time and detail, and in a commercial environment, sampling over a certain size may not lead to generally lower control costs than smaller ones. Environments can be massive or small, and scouting over a certain percentage of the total area may be considered too costly for one, but entirely feasible for the other, depending on their resources and pest pressure. Cultivators with years of scouting data might notice an uncharacteristic influx of pests and establish populations over a short time, and decide that it is more cost efficient to increase sampling, increasing the chances of detection, quickening potential control time at the end. For instance, in a section of 20 rows, each of the 11 units per row the hypothetical scouts evaluate is 1/220th of the whole, or 0.45% of the crop. Let's say that in one of these sections, a population of spider mites established in this small 1 square meter area. If the scouts decided to scout in the same pattern every week, they may miss the population for several weeks as it built up. Most pests are problematic specifically because they reproduce so fast, and under the right conditions, populations can double, sometimes before the next session of scouting. By the time the population has expanded into sampled areas, it might require heavier treatment controls, if they're available. Generally speaking, the closer a sample size reaches 100%, sometimes referred to as a census, the more precisely it might depict a population. The point at which no new information is gained from increased sampling data is called the saturation point. Since crop environments tend to be dynamic, especially the less they are protected from the external environment, that saturation point can change over time in response to the environment. For 10 years, the aforementioned scout group may find that their sampling rate allows them to deal with their average rate of pest pressure before it reaches the economic threshold. They may have even found that increasing the rate of sampling yielded no significant increase in pest detection. Over the span of a few years, however, conditions may elicit changes in pest pressure, such that their rate of scouting is inadequate for catching pests. Hotter environments will dramatically decrease the development time of many pests, and this typically leads to populations growing much larger both inside the crop space and outside of it. This is common at certain times of the year, and crop scouts should be aware of the yearly rhythm of the pest species with which they are familiar. Given enough time, short-term changes in environmental conditions may cause the local pest population to grow immensely and ingress into the crop area in large numbers, and this can necessitate extra proactive measures. Long-term change in climate, however, can increase or decrease the typical pest development time. If that time decreases, it may mean that the pest can be expected to spread much more rapidly than was typical, and induce damage at an even greater severity in the same amount of time. For some crops, this can be massively detrimental, depending on the pest in question. All of this is to say that cultivation conditions are in a constant state of flux, and crop scouting strategy must change in response to its dynamism.